Sorry. Good morning, guys. Just so you know, I'm a little bit sick, so my voice is going to sound super weird, but we'll get through this together. Really quickly, I want to again acknowledge your resilience and perseverance through this tough year with different teachers and transitioning and then having to learn this way, and then having Coach Reese have to go into the hospital with his baby and wife, and y'all are just amazing. You haven't complained once, and I don't know how you do it, but I'm super, super thankful for that, and very, very, very proud. Just to let you know, too, this is going to be the last chapter that we do. We'll take a test on it probably at the beginning of next week, and I'm going to have to get somebody to, maybe Miss Tammy can help me out with this, to let me know what the exam exemption policies are, so I can know who's going to be taking the exam and who will not be. Also, I don't have your grades. They took my name out of the book when I moved up here, so Coach Reese has been putting your grades in as you go, so I'll need to be able to just have the names of the people who are going to be taking the exam. That can just be later next week, that's fine. And then what the day the exam is, that would be great if somebody could give that to me. But yes, like I said, first of all, I am so proud of you all. You guys have done a great job. Second of all, this is going to be our last chapter that we do together, which is great. Getting 13 chapters in your first year of physics is a good job. A lot of high school students don't take physics before they go into college, and a lot of them end up having to take it as being medical majors or something like that. All right, so yesterday you did some practice problems. I'm sorry, I was traveling all day and didn't get in until 6 a.m. So yeah, I hope you were able to practice a little bit with those problems, and it'll help you when we get going on our test. Tests will be very similar to the way they always are, so don't worry. You guys always do great on them, and I'm sure that you will again. What I'm going to do first is I'm going to go over the 13.1 review, because I find that to be really important, because instead of just teaching you how to take tests, some of my goals are to teach you how to think critically. So like if you go to calculus, it's like, okay, the derivative of sine is cosine. That's great. We know that, but what does it mean? Like, what the heck does it mean, you know? Like, why is finding the slope of a tangent line important, which is what the derivative actually is. So I think that that's what some of this like 13.1 review does. It helps you think, okay, well, this is this, so why does that matter? Or, so if I have something like this, how can I apply that concept? So I think that's what this does. That's why I'm going over the 13.1 review. There are a few on here that are difficult that aren't going to be on your test, like 1.2 and 1.4, like they're helpful, but they aren't going to be something that's going to be on your test. They're a little bit more advanced, okay? But let's look at 13.1 review, and then we'll go, sorry, I'll just give you a little bit of the what we're going to do today. Then we'll move on to 13.2, and we'll go and I'll teach you how to find linear expansion. We'll go over the example problem and the rest of chapter 13.2 tomorrow, though. So it'll be a little bit of a light day with no homework, and and then we'll get going a little bit more on that tomorrow, which will be Thursday, and then we'll get your study guide on Friday, and then we'll go over the study guide Friday, and then take your on Monday, and then take your test on Tuesday. And then the rest of the time will be studying for exams. If you don't have to take the exam, studying for other exams, or reviewing or finishing up other work, okay? I'm not going to be too hard on you the end of this week, because I know that teachers are also trying to get those last tests in, okay? So when we finish the lecture today, help Miss Tammy out, and don't be loud, and just study the rest of other classes that you might need to study, okay? I'm trying to give you some time here, okay, to catch up towards the end. You guys are almost there. So close. I think it's the 3rd, so like 15 days. I have 9 days, you have 15. So, yeah. All right, so let's do this. All right, so if you look at page 313, under the section review, you have 1.1. It says you have 2 boxes. One is 20 centimeters by 20 centimeters by 20 centimeters. The other is 20 by 20 by 40. So it says, how does the pressure of the air on the outside of the 2 boxes compare? All right, so you need to know the equation for pressure, okay? And when you know the equation for pressure, so the pressures are both going to be the same then, because pressure doesn't depend on the size or the shape, right? So that's why pressure doesn't matter. It's going to be different with part B, though. It says, how does the magnitude of the total force of the air on the 2 boxes compare? Okay, so force is going to be proportional to surface area. So since one is 20 by 20 by 20 and one is 20 by 20 by 40, the surface area is going to be different, okay? And so the surface area of the first box, so you have 6 sides on a box, right? So it would be 6 times 20 by 20. And that's going to give you 2,400 centimeters squared, okay? And then of the second box, you have 20 by 20 plus, but you also have times 40, right? Okay, so for 2 of the sides, it's going to be 2 times 20 centimeters times 20 centimeters, plus 4 times 20 times 40. Okay, so that's the other 4 sides of the boxes in there, and 4 sides of the boxes are going to be 20 by 40, so that's why you have it work that way. This one's not going to be on your test either, because it doesn't, the surface area is a little bit weird to calculate sometimes. So this is just trying to help you think through the force definition or equation and the pressure definition. Okay, this is all this is really trying to do, and I just want to help you have all different angles to look at a problem that you can. So if you get confused on a test a little bit, you can be like, okay, well, I know that this, and I know that this. I might not know the answer correctly here, but if I look at it from this different angle, then, maybe I can be able to figure it out. Okay, so therefore the surface areas are different. So one is 2,400 centimeters squared, like I said, and then the other one is 4,000 centimeters squared. So if you divide those two by each other, 4,000 by 2,400, you get 1.67. Okay, so that means that the force is 1.67 times as much on the second, okay, because it's higher. So it'd be 1.67 times as much. You just divide those two together. I really hope y'all can hear me with my voice. I'm really sorry. All right, so let's look at 1.2. It says, does a full soft drink can float or sink in water? You can try it if there's a way that you can do that. I'm sorry, we, like I said, haven't been able to do as many experiments and things like that as some of the other physics classes, but I think you still have a great base. Okay, so does it matter whether the drink is diet or not? All drinks cans contain the same volume of liquid, 354 milliliters, and displace the same volume. What is the difference between a can that sinks and one that floats? All right, this one's kind of cool. So, of course, the mass is going to be less for a floater. A floating can is less dense than water, okay? So that means it has to have a density less than 1, because we know that the density of water is 1, okay? So a sinker is denser than water because the can volumes are the same. The masses of the cans have to be different then, right? And that way you'll know if one sinks or one floats, because the mass is going to be different. So actually another thing to try and keep this, try and remember this could be like a bonus or something. It's just a little fun thing to know. So artificial sweetener in a diet drink has less mass than corn syrup, which it makes sense if you think about it. But yeah, that's something that's kind of cool just to know. Okay, so let's look at 1.3. When a baby had a high fever, some doctors used to suggest to gently sponging the baby off with rubbing alcohol. Why do you think that this could help? Okay, so we looked back at like what volatile liquids are. So alcohol is a volatile liquid as well. So it will evaporate quickly and it'll cool the baby's skin. So that was one reason that doctors would suggest it, because it could cool them down rather quickly, right? All right, so let's look at this critical thinking problem. It's kind of a cool one. It says, it was a hot, humid day. Bess sat on the patio with a glass of cold water. The outside of the glass was coated with water. Her younger sister Jo suggested that the water had leaked through the glass from the inside to the outside. Suggested an experiment that Beth could do to show Jo where the water came from. So this one's kind of cool what they came up with here. So they suggested to add food coloring to the water. Okay, so if you add food color to the water inside the glass, does the water on the outside become colored? If the glass is in the refrigerator, does it get coated? If not, why wouldn't water leak through there? Put the glass out on a hot, dry day. Does it make any difference? You can set a cold metal object out in the air and it will become coated with water as well. Okay, so just add food coloring. Teach somebody that way, okay? That one won't be on your test or anything either. I just thought that was a cool little example. All right, so we've talked a lot about liquids in this first chapter, so we're going to look at the solid state now, okay? And like, how does a liquid differ from a solid? You know, there's some obvious things, but we're going to look at some more things today. So solids are stiff. You can push them. Liquids are soft. Can you rest your finger on water? Does it go through? Things like that. But then there's also times where like a liquid can feel like a solid, right? So has anybody done like belly flopped into the pool or whatever? You know, especially if you're at a higher distance, it hurts, right? So in that, like, it feels like you could be landing on solid, right? Yeah, so that's a time where they could seem the same. So let's look at solid bodies. So under certain laboratory conditions, solids and liquids are not easily distinguished, actually. As suggested, if you look at the computer images in 1315, down at the bottom of page 314 right there, researchers have made clusters containing only a few dozen atoms. These clusters have properties of both liquids and solids at the same temperature. Studies of this strange state of matter may help scientists as to invent a new useful material in the future. Never mind, I was going to tell you something, but that has to do with physical chemistry that y'all might take later, and that doesn't really matter. So when the temperature of a liquid is lowered, the average kinetic energy of the particles is lowered, right? So that the particles aren't moving as rapidly, because kinetic energy has to do with movement, right? So as the particles slow down, the cohesive forces become much more effective, and the particles are no longer able to slide over one another. So the particles become frozen into fixed particles called a crystal lattice, shown in figure 1316. It's on the top left of page 315 right there, okay? So although the forces hold the particles in place, the particles in a crystalline solid do not stop moving completely. So instead of moving, they vibrate. So they're still moving, they just aren't sliding back and forth across, right? So they vibrate around their fixed positions in the crystal lattice. In some solid materials, such as butter and glass, the particles do not form a fixed crystalline pattern. These substances, they have no regular crystal structure, but have a definite volume and shape. So those are called amorphous solids. So think about, like, maybe on your test, I might ask you to give me an example of an amorphous solid, okay? So look at that. You'll see butter and glass, okay? Give me those two. You'll be solid and good to go, okay? Amorphous solids are also classified as viscous or slowly viscous or slowly flowing liquids. Sorry, again. So let's look at some of the effects of freezing liquids, okay? So as a liquid freezes, its particles usually fit more closely together than in the liquid state. Solids are usually more dense than liquids. However, water is an exception because it is most dense at 4 degrees Celsius. As water freezes, the cohesive forces between particles decrease and the particles take up more space. So at 0 degrees Celsius, which is the freezing point of water, right, or of a liquid, ice has a lower density than the liquid water, and that's why it would float. Okay, so that's why you see icebergs and things like that. They float because of that. So for most liquids, an increase in the pressure on the surface of a liquid increases its freezing point. Water, again, is an exception, okay, because water expands as it freezes. An increase in pressure forces the molecules closer together, and it'll increase the cohesive forces among them, okay? The freezing point of water is lowered very slightly then. So people have suggested, too, that the drop in the water's freezing point caused by the pressure of an ice skater's blades can produce a thin film of liquid between the ice and the blades, which makes them move so effortlessly. So that's just a suggestion or a hypothesis. So you can look over here, the skater. It's Kristi Yamaguchi, I think, when she was younger. Some calculations of the pressure caused by even the sharpest blades showed that the ice would still be too cold to melt, but more recent measurements have shown that the friction between the blade and the ice generates enough thermal energy to melt the ice, and it can create that thin layer of water. If you've ever tried to walk on ice covered with water, you know how slippery it is. We're actually still dealing with a little bit of that right now. You'd think it would not be that way in Chicago, but it's the worst city ever when it comes to the weather. We had a frost advisory this morning. It's May 3rd. Come on, Chicago. The explanation is supported by the measurements of the spray of ice particles, such as those in the photo of the ice skater at the beginning of the chapter. So if you want to go look at that photo, go to the beginning right there, okay? Which are considerably warmer than the ice itself. The same process of melting occurs during snow skiing. I don't know if any of you have ever been snow skiing, but it's not easy. It's not as easy as water skiing. All right, let's look at the elasticity of solids. So external forces apply to a solid object, and they may twist or bend it out of shape. The ability of an object to return to its original form when the external forces are removed is called elasticity. So, yeah, we'll talk about that in a second. If too much deformation occurs, the object will not return to its original shape. Its elastic limit has been exceeded, so it couldn't come back to shape because of its elastic limit. Okay, I'm sure this makes sense. Elasticity depends on the electromagnetic forces that hold the particles of a substance together. Malleability and ductility are the two properties that depend on the structure and elasticity of a substance. So gold is malleable because it can be flattened and shaped by hammering into thin sheets. So gold's weird. It's actually kind of soft. Copper is a ductile metal because it can be pulled into thin strands of wire and used in electric circuits. So that's just some cool things about the elasticity of a solid. Just kind of know basically what elasticity means and what that means for a solid. And there are times when elasticity has been reached at its maximum, right? And it can't go back to the way it was. All right, so let's look at 315 at the thermal expansion of matter. We're almost done here, okay? So I know today's a lot of talking, and I'm also kind of sick, so it's not very helpful. But yeah, we'll get through this chapter together and then be done. Temperature changes cause materials in both solids and fluid states to expand when heated and to contract when cooled. So this property is known as thermal expansion, okay? It has many useful applications, such as using a thermometer to monitor your body temperature. As the mercury expands up a glass tube, when heated, all forms of matter, solid, liquid, or gas, generally become less dense and expand to fill more space. When the air near the floor of a room is warmed, gravity pulls the denser, colder ceiling air down, which pushes the warmer air upward. So that's why a lot of people, when they're looking for homes and it can be in a cold place, like maybe like Chicago here, A lot of times the really high ceilings aren't great because heat rises. So the living room or dining room, whichever has the high ceiling, will stay cold because the heat will rise. So this motion results in the circulation of air within the room called a convection current. Expansion allows liquids to be heated rapidly. When a container of liquid is heated from the bottom, convection currents form, just as they do in the air. But cold, more dense liquids, they sink to the bottom where it's warmed and then pushed up by the continuous flow of cooler liquid from the top. So you can see that with boiling water, right? So those are thermal expansions in liquids, but let's look at thermal expansion in solids, okay, because we're focusing more on solids in this part here. So the expansion of concrete and steel in high bridges means that the structures are longer in the summer than in the winter. So temperature extremes must be considered when bridges are designed. Gaps called expansion joints are built to allow for seasonal changes in length. High temperatures can damage railroad tracks that are laid without expansion joints. If you look at 13-17, you can see the buckling of the railroad tracks because of the extreme temperatures there. So if you think of other materials like Pyrex glass for cooking and laboratory glassware are designed to have the least possible thermal expansion. Blocks used as standard lengths in machine shops are often made of Invar, metal alloy that does not expand significantly when heated. So large telescope mirrors are made of ceramic material called Zerador, designed to have a coefficient of thermal expansion that is basically 0, okay? Down at table 13-2, you can see coefficients of thermal expansions at 20 degrees Celsius. So you can see like aluminum, iron, steel, glass, the soft glass, the Pyrex glass, all of that. So you might need to have this for your test. So I'll make sure that somebody scans this off for you guys. So the change in the length of a solid is proportional to the change in temperature. If you look at figure 13-18, okay, the change in the length of a material is proportional to the original length at and the change in the temperature. A solid will expand twice as much if the temperature is increased by 20 degrees Celsius than if it is increased by 10 degrees Celsius. The change is also proportional to its length. A 2-meter bar will expand twice as much as a 1-meter bar. Just telling you the proportionality of all of these things, okay? The length L of a solid at a temperature T can be found with the following equation. So you have the length 2 equals length 1 at alpha, is what that is. Length 1 times T2 minus T1. All right, that'll be important for us to know, especially tomorrow, but we're going to go over how to do it today. Okay, L1 is the length at temperature T1. Okay, that makes sense. They're proportional, right? And the alpha kind of looks like half of the infinity sign, kind of. Is called the coefficient of linear expansion, okay? So using simple algebra, the coefficient of linear expansion can be defined by the following equations. So we take that original equation, we got our L2 minus L1 equals the coefficient times L1 times the difference of temperature, right? So you just move those around, or you make it, first of all, it's change in L equals coefficient L times change in T, right? And then just to get, the coefficient by itself, just divide by the L1 and then do the same thing again with the change in temperature, and you'll get the coefficient of linear expansion by itself, or the change in L divided by change in L1 times change in temperature will give you the coefficient of linear expansion. So therefore, the unit for the coefficient of linear expansion is 1 degree, or C to the negative 1, okay? The coefficient for volume expansion, B, which is beta, is approximately 3 times the coefficient of linear expansion because volume expansion is 3-dimensional. That's kind of neat. The equation to determine volume expansion is change in volume equals the coefficient of volume expansion, or beta, times volume times change in temperature. Okay, we'll put these equations together a little bit tomorrow. There's not much left in the chapter, so I want to save that for tomorrow. So that's pretty much all we're going to go over today. Like I said, I'm sorry it was a lot of talking, and if I seemed a little scatterbrained, it's just because I'm not feeling 100%. But yes, for the millionth time, I'm so proud of you guys and all of the things that you have dealt with and done, and you guys are so close. Like, people don't think sometimes that high school can be a big time to graduate and things like that, but this is a 13-year process that you guys are about to finish, going all the way from kindergarten. There's finally an end in sight, and you get to move on and have a little bit more independence and become more of adults than you already are, and that's an exciting thing, something that you should really, really, really be proud of. I know that I'm proud of you. I know that the other faculty and staff are proud of you, and your parents and your siblings. So take some time to be proud of yourself too, because it's a very, very big accomplishment, and great thing. I know that y'all are all going to do great things for this country and for this world, and I can't wait to hear all about it. I got my first graduation announcement yesterday, so I'm super, super excited for you all. All right, you have a great day, and if somebody can get back with me about the exam rules and things like that, that would be really great. Yeah, so I will talk to you all tomorrow, and we'll finish up 13.2, and that'll be great. All right, you guys have a good one.